Hello everybody. So today I will take the class on reactions of carbocations. Okay. Carbocations can have four basic types of reactions. They can have four basic types of reactions. First one is combination with a negative ion. With a negative ion, you can say nucleophile or nucleophile. So first one is there are four basic reaction types of carbocations. First one is combination with a negative ion. Second one is elimination of a proton. Elimination of a proton. Okay. Second type. And third type is addition to an unsaturated linkage. You can say addition to a carbon-carbon multiple bond linkage, or you can say a multiple bond. Okay. Addition to a multiple bond. For one is rearrangement of their structures. Okay. Structural rearrangement can take place. So these are four basic types of reactions for carbocations. So I'm repeating again. The first one is combination with a negative ion, nucleophile. Second one is elimination of a proton, and the third one is addition to an unsaturated linkage, or you can say addition to multiple bonds. And fourth one is rearrangement of their structures, and structural rearrangement takes place. First two are gives neutral products, whereas last two reaction gives another carbocations. Okay, so these are about the reactions of carbocations. Let's see how the reaction takes place one by one. Let's see. Okay, let us see one by one. First one is combination with a negative ion. Okay. Combination with a negative ion, or it's a nucleophile. This is simply just opposite to the generation of carbocations by heteroactive fission. So here, one example is the carbocation reacts with another one nucleophile, or is a negative ion, anion. So we got this. So this is just opposite the generation of carbocations by heteroactive fissions. So many examples are here. You can have CH3, CH3, then CH3. Let's say this CH2, or you can have many positive charges. You can have here positive charge, yeah, and then plus chloride ion. You can have CH3, CH3, CH3. This Cl. Okay. So this is a carbocation combined with a nucleophile or negative ion to get this product, or to get a neutral product we got. Okay. The second one is elimination of a proton, elimination of a proton. Second one is, except for many examples are here. There's a common example, say C, the one Z. There's a hydrogen here. Then you can let's say this is a carbocation form here. Okay, let's say carbocation is formed here. So by this, so by removal of this proton is removed, so you can get this type of product. Okay, neutral product of 10. So many examples are here. You can have one example. This is for removal of the proton, or elimination of the proton. Second type. Okay, second type one. And so here one examples I'm giving here. So we have CH3, CH2, CH3. Okay, CH2 or CH2. Okay, here. So here protons are removed to get the more stable carbocation. To get the more stable carbocation here. So here one hydrogen here. So move here. So it gives CH2, CH3, CH3, CH, positive charge. So my here one is removed from here. Okay, transfer or migration like that. So it comes from, you can come from here. So you can come from here, CH3, CH2, CH2, or you can say any AX or Cl or bromide, okay, and sodium hydroxide reaction with OH, or you can say chloride, okay, potassium hydroxide, or any OH group. Okay. So remove this one, and remove a KBR, then positive charge we got, and migration takes place. Okay. So here, this one. So removable hydrogen can take place. Then we can have another one, addition to, then we can have another third one is addition to multiple bonds. Okay. Addition to multiple bonds. To multiple bonds. Or you can say unsaturated linkage. Okay. So here, very common word here. So let's say this one, the carbocation. Then we can have unsaturated bond here. So here, so first move this way. So we got another carbocation. C R C C C. Okay, positive charge here, carbocation. So this is one example how we can have like earlier one. So you can have this one. CH3. You can see CH3 positive charge here. Okay, then link with this CH3 double bond CH CH3. Okay, this is CH3. So here link this first. So you can have product will be CH3. These are all CH3. Then link this one, CH3, and then CC positive charge like this. These are CH3. Okay, so these are examples of addition to multiple bonds. So you got this also, you can get another carbocation. Okay, reactions of a carbocation or addition to a carbocation to multiple bonds gives another carbocation. So this then we have fourth one is rearrangement of carbocation. Okay. We can say fourth one is rearrangement to their, we can do of their structures. Okay, we can have detail, in detail we can do this one structure. I'm giving one example, say here. So let's say rearrangement takes place. So like this. So only another, you can give another carbocation. Okay. So it's 2R. So that's all. We'll do the detailed reactions of this. There are many types of rearrangements of carbocations. So we can in detail we can do it. So here let's see this. Discuss the rearrangements of carbocations in details. Okay. Rearrangements of carbocations. Rearrangement of carbocations. Okay. So let's say now discuss. So rearrangement carbocations means takes place to keep the more stable carbocations. So we can have rearrangement takes place. Rearrangement of carbocations takes place to keep a more stable carbocation. Okay. A more stable carbocation. So we can have different types of rearrangement here. First one is 1,2 hydride shift. 1,2 hydride shift. Okay. 1,2 hydride shifts. We can have this hydride can be shifted from here. For example, say H3, C, and then C, you can say hydrogen here, and CH3, and then there's a CH2. Okay, this is primary. This is primary carbocation. So here hydrogen can shift from here to here to get a more stable carbocation. Here this is not migrated because it is secondary. So here hydride shifts express. This hydride is migrated 1, 2. This 1, 2. 1, 2 positions. Okay. So CH3 and then CH3 becomes CH3 and then now become positive charge. So it gives this is primary carbocation, this is tertiary carbocation. So hydride shifts, hydrogen can shift. When you shift methyl groups, it can give secondary alcohol. So this is hydride is better than secondary alcohol. That's why it gives the more stable carbocation. Okay. So if we have methyl group shifts, then we can have secondary carbocation. So we can this one is the more better than this because primary is less stable than compared to tertiary carbocation. Tertiary carbocation is more stable than this than primary carbocation. Now let's have another rearrangement, a very common one, neopentyl rearrangement. Okay, second one is neopentyl rearrangement. Okay. This is commonly known as, altogether known as Wagner Meerwand rearrangement. Okay, this is commonly known as Wagner Meerwand rearrangement. So neopentyl rearrangement. So here we have, suppose I will give examples. H3, same here. Common name is CH3, that I have given earlier one. It's okay. This is known as neopentyl carbocation. So this one undergo rearrangement to give this methyl group migration takes place to give this H3, CH3, and this positive charge here, and CH2, CH3. So this is primary carbocation, and now this is tertiary carbocation. So neopentyl rearrangement is neopentyl carbocation undergo rearrangement to give the more stable carbocation. Okay. So from this, then you can have other reactions. So examples, many examples are here in the case of neopentyl carbocation. So for example here, when this compound is from, we can get from many reactions, from neopentyl reactions, from let's say alcohol, reactions with alcohol, CH3, CH2OH. Okay. Alkyl alcohol, so you can check 1,2,2 dimethyl, 2,2 dimethyl, 1 propanol. Okay. In presence of acid, this is protonated, and the loss as water, and you can get this 2,3, this neopentyl CH2, neopentyl carbocation of God. Okay, this sulfuric acid is protonated, you come to OH2, the loss water, minus water, gives this one. So this can give further reactions with, can give loss of this, it can give final product will be C, this migration takes place, and then after the loss of this, okay, this one, okay, CH3, this CH3, you can have another one hydrogen here, and CH3, okay. First step is migration, and then loss of proton, okay. Or you can say water is lost. So this from you can check that neopentyl rearrangement can take, Wagner Meerwand rearrangement can take place from alcohol. Then from alkyl bromide also, you can, same compound can take alkyl bromide, some substituent, CH2, Br. Okay, here the reagent is silver hydroxide. So you can change by reacting silver hydroxide, so you can give silver bromide. So you can choose this from a silver bromide will go to neopentyl carbocation, and then finally if the product hydroxide, so product will be, I like the product. Okay, so here final product will be CH3, OH will come, water will, OH will come, attack here, OH, that silver hydroxide will take, then CH2, CH3. So first migration takes place from here to migration, and then positive charge comes, then OH attack here. So this is the final product. Then another one by double bond. So even unsaturated compounds can also undergo neopentyl carbocation rearrangement. Even alkyl compounds. So I'm giving one example. Similarly here, CH3, CH3, and then you can have CH3, and then CH, number one CH2. Okay, alkane. So okay, 1, 2, 3. The 3 dimethyl, 1 butene. Okay, 1, 2, 3, 4. 3 dimethyl, 1 butene. So you can undergo reaction with HCl. And so pass step will be like this. Then you get a positive charge here. So I will write okay, reaction like this pass HCl. Okay, this will get the form here. Then you can have CH3, 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 CH, then it becomes CH3 here, so it becomes positive charge. Now it is secondary alcohol, secondary carbocation. So migration takes place. So here migration takes place to give this positive charge here, CH3, CH3, I think you can CH, you can have one CH3 here, CH3 and CH3. Okay. So this is now is the tertiary carbocation. Okay. So rearrangement takes place from secondary to tertiary carbocation. So this can, the hydrogen can lose, so it can give minus H positives, hydride loss. This means removal of hydrogen, hydride, or you can say removal of hydride or hydrogen. Removal of proton, you can say removal of proton, you can say product will be double bond will come here, C, 2, 3 dimethyl, 2 butene, 2, 1, 2, 3, 2, 3 dimethyl, 1 position here, 2 position, and 2 position CH3 here, the CH3, because CH3. So 1, 2, 3, 4. You can say 2, 3 dimethyl, 2 butene. Okay. So here another example, we got the product from here like this. So you can undergo through your pentan rearrangement. So Vietnam rearrangement. So these are the examples I'm giving. So we can try many reactions are here in the veterinary Mervyn rearrangement. Many reactions are here. So you can undergo many types of reactions like alcohol reaction also. So you can undergo 2, 3 rearrangement can take place. For example, one example I'm giving. Say for example this one. This is CH, or you can say, or let us say OET, ethyl groups, and this OH hydroxy group. Okay, in presence of acids, so protonation takes place and loss minus water. So you got a carbocation here, C ethyl group, positive charge here, so loss of water. Okay, protonation, then loss of water, you got this carbocation. Then this carbocation undergo the ring expansion takes place. So you got 5-member ring from 4-member ring to you can have 5-member ring. Okay, positive charge here. Then another you can shift another here again, migration takes place. So you can have 2 or 3 types of migration can take. Ethyl groups here, and another ethyl groups here. Then we have positive charge here. Now here is hydrogen here. So migration, another ethyl group migrated. Then finally loss of this proton, removal of proton, or like earlier one, which we can have one of the reaction type. Okay, so we can have ethyl groups in the bottom here. This is the products. So this the type of compound can undergo 2 or 3 types of rearrangement to keep the final product. Okay. Now we can another examples we can have also. You can try this also. This thiophene substituent CH2 Cl, okay, in presence of HCl or sodium oxide. So you can try this reaction, or you can just silver hydroxide. Okay, this is silver oxide better. So this one, first remove the silver chloride, positive charge will come, then ring expansion will come. Okay, so you can try these reactions also. And then another reactions I can give important reaction, another examples of Wagner-Meyer-Wine rearrangement. Okay, so here, suppose for example we have this 6-member ring 2, you can convert to 7-member ring. How it goes to 7-member ring? Okay. So you can have first, many methods are here. First one you can try with hydrogen cyanide, or you can try nitromethane, or you can reaction this one. And then second one is reduction will take place by reduction of this one. Reduction, and third one is after reduction, then migration, then migration takes place, and you can have hydrolysis, or you can have many types of reactions you can have. Okay, so here first reaction is hydrogen cyanide, or you can react with nitromethane, and then you can get reduction with, and then cyclization takes place. ICNO3 by water, or let's see, first one, let's see here, CH3 or NO2, let's say nitromethane reactions with CH3 NO2. We can react with hydrogen cyanide in presence of hydroxide ion. Okay, so I am giving this mechanism of the reactions. So OH will come, this will attack here, CH2 and NO2. Okay, this will be reduction takes place. Reduction of this one, you can get this OH, then you can have CH2 and H2. Then you can from by this sodium nitrite, you can have third one is sodium nitrite, third one is sodium nitrite. Why this one? Okay, ICL, and this is 4-1 hydrolysis. Sodium nitrite, the azo molecule will form ICL, so it gives OH. So you get CH2 and triple bond end. Okay, positive charge here, Cl negative charge. So loss of this one, you can get carbocation here. 5-member, okay, I know the idle here. Okay. So OH here, and here's CH2, positive charge here. OH. Okay. So now we got a positive charge. Now ring expansion takes place this way. Ring expansion takes place. So you can have, I think you can see. So ring expansion takes place. You can 6-member 2 will come 7-member ring. So 6-member 2 will come to 7-member ring. Okay. So you got a OH here, positive charge here. The loss of this one can give minus loss of proton or removal of proton, then you can get the final product. 7-member ring. So ring expansion takes place. So what? From cyclohexanon to cycloheptanon. So in this way you can combine these reactions. Also these are undergo through the carbocation. So Wagner-Meyer rearrangement. Another example for Wagner-Meyer rearrangement. Now let's come to final. There is another rearrangement. Another rearrangement of carbocation. There is pinacol rearrangement. Okay. Pinacol rearrangement. Very common rearrangement. We can have another rearrangement is pinacol rearrangement. Pinacol rearrangement. So here rearrangement 1,2 diols undergo rearrangement. Okay, 1,2 diols undergo rearrangement to give ketones, pinacolone. So here 1,2 diols, conversion, you can say conversion of 1,2 diols into ketones, conversion of 1,2 diols into in presence of sulfuric acid, or you can say acids, in presence of acids, sulfuric acids, 2 ketones. two ketones means mostly pinacolons. Pinacolon is known as pinacol rearrangement. Okay, pinacolon rearrangement. So I'm repeating again, 1 to dose undergo rearrangement to give, suppose there's R here, so O is here, O is okay. So R is migrating group. So here in presence of acid, sulfuric acid. So one of these proton attack. So here it gives migration takes place. So you got this type of like this ketone. So you can have migrating groups here. R is migrating group. Then you can have, so R migrated here, then you can have this one. So from 1 to dose to ketones. Okay. To convert this is generally it is known as pinacol rearrangement. Pinacol rearrangement. So conversion of 1 to dose in presence of acids to give the ketone is known as pinacol rearrangement. There are so many rearrangements takes place. So I'll give many examples here for pinacol rearrangement. So for examples, many examples are here. Okay, CH3, we can have CH3 or CH3 or symmetrical compound, OH, okay, sulfuric acid. So it is symmetrical here because so many can give some migration takes place. The methyl groups migrate here. Okay, CO, CH3, CH3. Okay. So here one example is, and if they are unsymmetrical or another one asymmetrical one, phenyl group here, and then we have CH3, phenyl group here, OH. So here methyl group migrates, but here in this case phenyl groups migrates. So phenyl groups migrate to give the more stability. The same is symmetrical also here. Symmetrical, so you got a same carbocation. So here, due to migratory aptitude, phenyl group migrates. So here, CH3, COO, C, so phenyl, and methyl groups. Okay, CH3. So phenyl group migrates. Another compound, not methyl here. Okay, it's gonna be methyl migrate methyl group doesn't migrate. Suppose if you have in this case also here, another examples I'll give here. Suppose we have phenyl groups are here, and this OH, and here methyl groups are here, methyl groups, OH. Similar here also is unsymmetrical when you put a sulfuric acid. So here, when you lost this one, water, you got a carbocation here. When you lost this one, you got a carbocation here. But here, this carbocation is more stable than this one. For a tertiary carbocation, but loss of water from here will give a carbocation which is more stable than the loss of here will give the more carbocation from here. So that's why here methyl group migrates. Okay, so you got phenyl, phenyl, and methyl groups migrates, and then you have stable compound methyl. Okay, CH3. So here, in this case, phenyl migrates, Me migrates. Okay, here phenyl migrates. Depending due to the stability of the carbocations. In the first case, due to the migratory aptitude. So here you can have due to migratory aptitude. Okay, phenyl migrates. But here due to the stability of carbocation. Stability of carbocation. Okay. Cation. So here OH group lost from here will give. Sometimes hydrogen also migrates. If hydrogen also can migrate from here. So let's see here. Let's say here hydrogen here, and then hydrogen here. Okay, we use H2 sulfuric acid, H2SO4. So if you lost this one, water, you get a primary carbocation. If you lose this one, you got tertiary carbocation. Tertiary carbocation is more stable than primary carbocation. So here lost this one, then migration takes place. So you got this H3, CH3, and you can see it's hydrogen migrated, and then you can have aldehyde. Okay. So here methyl doesn't migrate because the stability of carbocation obtained from here will be more stable tertiary carbocation from not from here, is primary. So hydrogen migrated here. So you got a carbon compound. Let's see the mechanism of this pinacone-pinachloride rearrangement. Pinacone-pinachloride rearrangement can take place. Let's say examples here, R here, migrating groups. Say OH. So first, protonation takes place here. So we got OH, okay, water, positive charge here, and loss of water. So we got a carbocation, R, OH, okay, C. So we got a carbocation here. Then migration takes place. Then okay, I'm giving general example only. Okay, so here R migrated, then here positive charge will come here. So here the loss of proton or removal of proton, so you can have this. So you can have this R, C, C. Okay. So this is general mechanisms. So the R depending on the R, nature R. So let's see what are the features of pinacone-pinachloride rearrangement. Pinacone-pinachloride rearrangement have some features. Due to the stability, migration takes place. Due to the stability of carbocation, first one, migration takes place. Migration takes place to give more stable carbocation. That's why I'm giving examples earlier one. Okay. So sometimes methyl group migrates, sometimes phenyl group migrates, sometimes hydrogen migrates due to the stability of the carbocation. Second one, migration can take place due to migratory aptitude. Migratory aptitude. Okay. So I'm giving examples like earlier cases. So here, say phenyl or methyl group here, phenyl group here. This is OH group. So methyl groups, phenyl groups, OH groups. You have symmetrical compound. So you have one is methyl, one is phenyl. So phenyl group migrates. So here, this way and this way. And then losses water. So you can mechanism is like this. So you can have in presence of this sulfuric acid. So you can have, so here phenyl groups migrate, not the methyl groups. Okay, because migratory aptitudes, methyl greater than phenyl greater than methyl groups. So here methyl, phenyl, and phenyl. Okay. Phenyl group migrates. So in the migratory aptitude, the order is phenyl greater than methyl. So among the aromatic compounds, then we can have OCH3 para positions. We can like this para positions greater than methyl groups here. So you can write down here phenyl greater than methyl. Okay, among the aromatic compounds, so greater than phenyl. Then we can have nitro is this one, okay, NO2. Nitro green groups are less. So methoxy is position more in migratory aptitude than paramethyl, than phenyl or paranitro. Okay, this is the migratory aptitude. And another feature is, these are features of one. Okay, another feature is anti-migration takes place when the migrating groups and then the green groups are. Third one is migration of the compound takes place. Migration takes place and in an anti-position, at anti-position. In trans, we can say trans position, trans. Okay, then is migrating group and living groups are anti-position. That is migrating group and the living group are in anti-position. So like this one. In the case of say you can have this season like this one, Caesar trans, you can have, let's say this is XL living groups, so they are in the anti-position. So usually so like this. Okay. So this example, okay. The migratory groups and this living groups are in anti-positions. This should be in anti-positions. So you can have L, R, OS. So like this. So it should be in the anti-positions. So these are examples. Even you can apply in the this Vietnamese management of coil. So this is third one. Third feature is this in the migratory groups and the living groups. They are in the opposite position. Okay. So many examples I will give here. Some examples of pinnacle resonance. So you can try this thing. Suppose five member ring. So let's say OS here and C OS. The methyl group CH3 in presence of sulfuric acid. So you can try what is the loss. Which one hydroxy group here or here will lose. So depending on here, this is more carbocation, here is more than this compound. Both are necessary, but here is more. So this will lose more carbocation here. So methyl group migrates. So first one. And second one examples, you can try this. Okay, this one you can try. So always here. Okay, so figure C2. So what is the mechanism here? So here is symmetrical, so one can be lost, then expansion ring takes place. So one here migration of the this thing. Migration of the bond take place. So this bond is broken down. And third one is we have season trans. We'll get season trans. Like on here. Season trans 1,2 dimethyl cyclohexane. Season trans 1,2 dimethyl cyclohexane. Another example says season trans 1,2. So let's say cis OS. Okay, cis positions here. Another one is okay, let's say cis3 here, OS here, and here OS trans position. Okay, cis3 trans. You can say the name of the compound is cis 1,2 position. Cis 1,2 dimethyl cyclohexane 1,2 diol. Cis 1,2 dimethyl cyclohexane 1,2 diol. Okay. So another one is trans. When you do the reactions in sulfuric acid, so they get different products. Okay. Well, you can try this one. One is in contraction, another one is undergo. These are all pinnacle resonance. Same mechanism takes place. So these are examples of pinnacle resonance. So these are about the about the resonance of carbocations. Now we have finally I will give one examples. Another is rearrangement. There is dienol, phenol rearrangement. Okay. This is another rearrangement of carbocation. So here rearrangement takes place in presence of sulfuric acid. So we say dienol, CH3, there's a CH3. Okay. In presence of sulfuric acid, it gives to phenol. Okay. OH and CH3. This is phenol, substituted phenol. So this dienol. Dienol means di means two. Okay. In means double bond. Two double bonds are here, di double bond, and one ONE means ketone. So two double bond and one ketone, dienone. So you have substituted phenol. So this rearrangement is also known as dienol phenol rearrangement. So how, let's see the mechanism of the reactions. So I'll write the mechanism of the reactions. Dienol undergo rearrangement to give the phenol. Okay. So one example, I mean, say C, C3, 2. Okay. Say first in presence of sulfuric acid, proton acid takes place, protonation takes place to keep this. So we got this C3, C3, and protonation of the oxonium takes place. Okay, positive charge. Now this will go. We have this one, this C3, C3, then we have OH here, then positive charge here. Okay, this position. So I got that. So here OH and positive charge here. So this carbon becomes positive charge. Okay. Then this again given this one. Then we have another resonance structures. So here double bond here, OH here, now here. Then we have positive charge here and C3, C3. Now migration takes place. So this is migrated. So you can have another carbocation, OH. Then migration takes place is C3. So we have hydrogen here. You can have hydrogen C3. Okay. Now it becomes positive charge. So loss of this sulfuric acid take up loss of proton or removal of proton by sulfur from hydrogen sulfide from sulfuric acid. So from there you get this final product. Okay. So this is the mechanism of formation of this phenol, substitute phenol, C3, C3. So this one. So here sulfuric acid you can write this O sulfuric acid. Okay. So you have this proton break up here proton, and you got negative charge. Yes. This negative charge OSO3 is okay. This will pick up this proton. Okay. So sulfuric acid will come. So this is the way how the rearrangement mechanism, the rearrangement of dienol phenol rearrangement. So dienol can undergo rearrangement to phenolic compounds by using in presence of sulfuric acid. So these are the rearrangement carbocations. So we have discussed reactions of carbocations and the rearrangement carbocations. So this is wind up. We'll wind up here about the carbocations. Okay. Next class we can have carbonyl. Okay.